Yeah, and then yeah. Okay. Everyone has this crazy Mac problem that just sometimes the microphone doesn't work. The amazing fix is just to go to System Preferences, Keyboard, and then the far right tab is Dictation on OS X. And then as soon as you just look at the dictation page, it sorts out your audio for you. Okay, peace. I got a subscriber. Hello, subscriber. If you watch this, I'm amazed. You know how good this is? Because obviously I'm not really here to say stuff that I want to make public. I want stuff here to be like, well, I said it before, when later this is still here. That's what I want. So I'm just amazed and blessed that a subscriber has come to my channel. It's the most silly thing that, you know, I know that this is an acknowledgement. You haven't made a statement about me. Thank you, subscriber, but acknowledgement, whatever. It's great. I'm speaking in my videos of what, like, science that hasn't been made up or verified to be true yet. So it proves that no matter who you are, if you make a YouTube channel, you can talk about anything. Because if I can talk about maths which hasn't been made up yet and still someone wants that, that's just precious and blessed. Thank you so much. So I'm in a pretty good mood today. My body is dying and I'm feeling about logic. I've been writing about exactly that point where you go, okay, well, every sentence has its own logical conditionality. Every sentence has the situation in which it's true. Maybe it's all the same if it's a tautology. Maybe it's sometimes if it's a conditional statement. And then there's also those paradoxes that can't ever really be true and consistent with anything. Okay, now the middle case is really interesting because instead of just having like, well, all the true things are equally true, the sometimes true things well, there's almost as many different conditions as there are different sentences that you can make which aren't always true or false. That every sometimes true sentence has its own conditional case, which in general isn't the same condition as all the other conditional statements. However, because we're allowed to make statements that are equivalent to any statement that we can think of really easily, and we could keep on doing that and like deferring them, we get this really unsurprising surprise that out of all the things we can say in logical arithmetic and out of all the things we can build up with these symbols, some of them mean the same thing, some of them don't, and that's not just a function of language. So with the minimal tools of inference, we get pretty quickly to some stuff is that way, but not because of what we assumed. Neatly, or more specifically, but we're in the ballpark of theorems where two different statements actually just refer to the same thing in the world. Now, as soon as that happens, we've got this amazing case where something is true in the world, which is affecting our language, and our language is able to tell the difference. It's amazing. And in fact, what we're doing is telling the difference by what our language can and can't tell the difference between. We can't ask this, does A prove B in one question, but we can ask, does A prove B in a few questions. If we start out with just a blank logical vocabulary palette and we have like A implies B, there's a whole bundle of things that can mean within different scenarios. For instance, the one that we're really interested in right now is where A, just by itself, if you were told A, then you would be able to derive B out of perhaps finitely many things that you could derive from A. Well, that's the next bit that we've got to do to formulate in the book part, which is going alongside the videos. And the making a book, no. The case where a theorem A really does prove a theorem B. Weird way to look at it, but you can therefore cut up A into two bits, A and anti-A for the moment, or just A tick, and then everything in A tick you're going to say is false. No. You're going to say it's ambivalent. What we need to do, if a part of A proves B and not all of it, which is we need not all of it to prove B for it to be an interesting thing for us at this moment. It means that I can take some of A, and that's going to prove B by itself. And there's this other bit that I don't need to prove A, or sorry, to prove B, but it's part of A. So what can I do about that if I've got a sentence and I know that there's some way of splitting it up into two parts. I can assign all of it, all of the bit I want in two variables. So I'm going to make a mapping of the expression B. I find some way of satisfying B with some variables, and then say I'm going to use only those variables and prove the exact same thing from A because I can. And maybe assign the rest of A some other variables, so we've made it distinctly the other thing. I was thinking it more like binary algebra, where what I want to do is take the bit that doesn't prove B, that's irrelevant for proving B, or just isn't necessary for proving B, and then add that to itself, so that all of my so that bit is just negated, that it'll all come out at zeros. Yeah. Do we have a function like that in logic? Of course we must. It's 0. I mean XOR? No. Oh yeah. If I add the two and then XOR them, then I'm always going to get a 0 where I want. Okay. So what am I doing? I take a statement A. It proves B. It doesn't require all of it to prove B, or else B would then prove A, and we're looking for the cases where it doesn't. A proves B implies, in this case, that you can split up A into two parts of A, right? So it just does imply, okay, A implies B. A proves B implies that A1 and A2, these little parts of A, such that A1, if and only if B, and A2 such that A and XOR A2 proves B. So we've found two different ways of proving the statement B. One of them by cutting up A, one of them by making invisible part of it that we'd specified. Is that any good? And then we have a way to find stuff that strictly proves stuff. Yeah, okay. So that's strictly proves in the sense that you're doing homework, you say therefore, and then your teacher gets to go, well, yeah, that really does therefore that, so I have to let you away with that. Right? Yeah. The other kind of implies, well, the weakest kind of implies that just this always happens when this happens, and it doesn't say anything about the conditions. But if you put that within any frame of conditionality and say we're not talking about the whole world, we're just talking about some of the time, then whatever you did to construct this condition around it and say, in this case, A implies B, then the very implies sign that's between that A and B, it means a different thing depending on what condition it's in. We soon bump into that there are going to be lots of questions that maybe logic can't answer. And then I always think that that's not going to be the case, but they're going to be interesting things to think about on the way. Spoilers if I'm right, or like we can prove me wrong. What happens? First off, every single implies sign that is logically distinct is logically distinct. Every time I have an implies sign that's logically distinct, I've got a new condition there. And if I have a condition that if I have a condition, I shouldn't be able to ever describe, perhaps, all of the different conditions in logic, because every single implies sign is going to have a different condition to it. So I would just need to make explicit all of the different conditions to have all of the conditions mentioned. It seems that there is not a way to do it overarchingly, except perhaps to say, well, everything that we're doing follows from this one assumption about implies. If that's the case, then we have a way of saying all the different kinds in this one boring kind that or amazing kind that satisfies all of them, and that's all we have. Um, there doesn't seem to be a way in between to make a here's logic mentioning all the different kinds of conditions it has, except for from its basic axiom. And actually, no, we've just proved that. That's cool. Um, there can't be another way, because if there was another way that you could prove all of the different conditions that you can get, it would have to look exactly the same as your axiom, and not just look the same as your axiom, it would have to be logically indistinct from your axiom. So the axiom is the way to describe all the conditions that you can have. That's very cool. Now, why is there going to be math out there? Because some of the times our logical sentences, they can be distinct in syntax, and they can not really share anything in common with each other at all in how they're presented, but still they're gonna be just true at the same time because of the rules of logic, because of stuff we didn't consider when we first made up this very, very weak axiom that A implies B means that B is always true when A is true. It's really all we're using, and we find, well, soon, mathematics just out in the universe. Or within the things that we can describe and within the things that has to be true. Why? How? We've got more meanings than things. And that'll do it. We've got more syntactical structures than stuff. So some of the syntactical structures have to overlap on the stuff. That really, really modest and low, humble idea is truth, where the syntactical structures overlap on the stuff. That's truth, and we have this metalogical way to say it, that if you can say the same thing twice without repeating yourself, then it is true, because there's nothing outside. You've proved that your identity isn't based on language if you've sufficiently satisfied you haven't repeated yourself. So the only way that these meanings can join up is in the world. Um, when you apply this to categories which are dirty logical categories, like up in the real world, like a picture frame or I don't know, stuff that you can't really tell the difference between if something is one of those or not, you get into, there might be lots of different ways that you can synonyms for the same thing, but you've basically repeated yourself. In logic, we get a clearer way of saying you haven't repeated yourself, which is what we've just done. The A strictly implies B thing. If you can take part of A, XOR it with A, and then you've got B. Yeah. Or is it enough to say that you've got a tautology with B? But that would be the when you're checking. Okay. Right, so we're at the bottom of theorems. We've got a load of interesting mathematical structures, and basically what I'm doing right now is trying to find how am I going to color in between those two bits. Because when we can talk about, once it's ready, once we've got the foundation, just go, here's the maths. We're going to go ping. Who knew all the maths so quickly? Like, I've wanted to teach all the maths at once, and I've wanted to logicize math, and these things seem real done. So how are we going to get from, we've got these intersecting structures that overlap, and here are mathematical structures. Mathematical structures, what are they? They're things that we can talk about, and their very meanings overlap over other meanings. That mathematical structures are always structures, relations over arbitrary points, and those relations are equally applicable to many different things. So there's even more relations between things than there are things, and if there were more semantic statements, or sorry, more syntactical forms that we could make out of logical forms than there were things. Now we're going to take into account all the relations between syntactical forms. We're taking into account the relations, but there's pi more. Okay. There's literally pi more. It comes up later that the number of coprime pairs there are divided by the number of whole numbers there are is pi. I got such a good proof on this, and by the time I'm done on circles, no one's going to doubt me on circles. It's the one thing. People are just, if Ish has a comment about circles, I'm usually correct about circles because I've made up lots of stuff about circles. Circles, so do we want to leap straight towards circles? That's a very good thing. We kind of need circles to do addition. We need to define a relation between a relation within our logic to be able to do circles, and once we've done that, we've got all the pieces to be able to define a relation where if you've got all the way around this semicircle, then you can start on the other half of the semicircle, or you can start on the other semicircle, and vice versa. Why is that good? Because otherwise, if you were doing it all in individual candidates, you would have to have like A implies B implies C implies implies A, but A isn't allowed to be all of the other points on the thing if it's going to be a circle. But you would get a contradiction if you didn't do it in terms of two relations, because you would have A implies A, but A is not A. Can't be done. So how are we making this bridge between this kind of wild idea about just some of the meanings overlap? There's got to be a world in place for that to happen. And here's our mathematical structures. It should be easy. How are these two things related? They're there. It's maths if you have them both. Have we not said it before getting derailed on pi? That there's more relations than there are things. So if there's more true statements than there are things, there's going to be more relations about true statements than there are going to be relations about things. Relations about true statements is first order logic, right? Well, we don't have different orders of logic if we're really doing the model extension thing. So the relations between true sentences, what's that? Well, let's say that's the hypermodal model logic. That's at least that area where we get to do all the logic stuff. And then the relations between those is that maths all of a sudden. Yeah, that's exactly what we've done. We've said here is a relation, and we're relating to relations, and the relating of relations is the model to the argument. So we've gone up in a strict. That's all. That's that. Thank you. That's all we need for today. Like, I have no idea what I just said, but it's the answer. Right. Once you combine relations, once you compare relations to relations, then you get more conditions. You get conditions which are conditions of both, and so there's going to be more conditions and more conditions, and every time you add an axiom, then it's going to give you more specificity, more stuff that you can say. Each of those can give you more conditions, and so whilst we're racing through this, by the time we get to the maths, we're going to be really interested in salient points. Uh, we're also pretty interested in salient points in the logic, but we haven't mentioned it. The beginning, okay, every structure that we're going to make sure that there's more than one object in this structure, we're always going to pack it out with an ordering and say A implies B implies as many as we need, and then in every case, because it's just how we're making numbers, we're also going to swoop back and say A implies B implies C implies not B, or not C implies B implies A. Doesn't work the other way around, and so you've definitely got three logically unique, distinct things. None of them behave the same way as each other. They're not in the same place as each other. It allows us to have this idea of locations. Then we've got this idea of A. As soon as we've done that, if there's ever a structure that you can say, well, I can identify 3 points on it and just imagine a path through them, that's all you need to describe a thing that has 3 points on it, and you can always do it backwards. Can you always do it in 3 different ways? Yeah, of course. That our implicature isn't, because it's not describing a direction on the thing that we're describing. Yeah, absolutely. You can start with the middle point and say B implies C implies A, just to have described your 3 points and to describe that there are indeed 3 things on there. So from the first time you describe anything, even whilst it's very like safe and certain to describe this abstract thing that has only 2 things on it, and that's it, 2 featureless things. There's not really anything simpler you can describe, but as soon as you describe even that within logic, and we make a model of it so that we can represent it and play with it, we have to make an arbitrary we have to make an arbitrary assumption at the beginning of order, that as soon as we've got an order to things, even before we've got an order to things, we could have always modeled it in a different order. We could have always said that the thing that we called special, A, isn't actually special, but B is special. Or like C is kind of special if you go A implies B implies C. So you could have A being the other kind of special that it was in the first way of typing it round. I'm not sure how to say it. Well, assignment of variables onto the thing being described. This isn't so necessary. Once we've got addition, we've got circles. We're at this point where we're comparing relations outright, A to B. So the next step for the book is to write about comparing relations in general. Now we've got a way to compare relations to see if they are, one proves the other within whatever context we're talking about. How to compare relations. Cool. So if I have a big long relation that says like A implies B implies C implies D, and then I say I've got alpha and alpha proves A and it proves D, has to prove the whole set, right? Yeah, but alpha also, or sorry, A proves all of that too. Can I say that alpha is not A? Is there... Whoa, that's interesting. I mean, we do this the whole time where we like slice conditions and then just infinitely many conditions come out at the other end. If I've got a structure, I know it exists, there's 4 things on it. It says A implies B implies C implies D, and not the other way around to make it easier. Then I say I've got alpha. Alpha implies A. Usually that means the alpha is A, because that's the only thing that implies A is A so far. But then we say alpha implies A, and it implies D. A already did that. But then if we say A is not alpha, what do we mean is not? If A... Okay, so yeah, it works. It seems sketchy, but it says that there's some distinction between A and alpha that isn't written down. We don't have a way to prove it, but it says that there is one. We can use that as a condition to say, okay, well, we've got all of these things that we couldn't see before that are different representatives of equivalence classes that it's like a model extension up. We've got all of the different variants of the same positions that we could talk about. What are we doing? Relations. Huh. If I take A implies B implies C implies D, and vice versa, not D implies C implies B implies A. And then I state A. I've stated the whole thing. I've stated everything A through D. Or have I? Is it merely that I can prove the whole thing? Is there allowed to be a logical distinction between A and all of those things? I feel like yeah, because you could mess up. Well, no, because A, we would want it to be replaceable with all the things it implies, right? That yeah, so I don't like that you would be able to say that there's a difference between A and D in that situation. But there is the difference between having completed a relation and having not completed a relation, or having made our whole way through a list and having not made our way through a list. I think the only way we can do it is by making 2 lists, and this is what we had before, and this is the link between a relation and a circle. If I have A implies all the way to D and not backwards, and I have alpha implies all the way to delta and not backwards. What about if I just ping it over here to X? I say delta implies X, and X implies alpha. What we need is not to be able to prove ourselves into a circle. So what would we have there? A implies, well, alpha implies all the way to delta. Delta implies this thing called X. X implies alpha. So, and we're going to do it again, that D implies Y implies alpha. So we've got Alpha implies delta, implies X, implies A, implies D, implies Y, implies alpha. And alpha is not A. And alpha proves A, and A proves alpha. No, we're going to get a contradiction then if we just say that A doesn't if and only if alpha, because anytime you have A, you can prove alpha. Anytime you have alpha, you can prove A. Yeah. We already have a way of comparing relations, which is to use variables which have been defined the way we're hoping works, with the find the non-trivial solutions to things. This is going to be a big part of what I'm hoping to publish or share, non-trivial solutions to things. So we had this problem towards logicization, towards trying to express math in logic. The big problem was that logic always makes the minimal assumptions, and if you have something like A and B and C, logic is always going to say, well, there is technically a true solution that A is B is C, and it's the simplest way to do it. Once you navigate around that by saying that, like, well, a tautology doesn't prove this, proves this, then it's like you're only looking for the cases which specifically aren't the ones that depend on naming the variables a certain way, and you can invoke I believe and do so hope, and it seems really consistent, and useful once you start doing it. What? I lost it. Seems good that, oh yeah, that we can identify that way a variable with a relation and say this relation has to behave like this. So one of these relations can prove stuff that's smaller inside it, that it doesn't name, so that all of these things, once they come together, yeah, that's going to satisfy the condition of this is going to satisfy the condition of all of that, and then if we have two of them, we can point them together as circles. So we're going to use our tautology doesn't imply scheme to do the thing that we wanted to do, link two halves of a circle together. Once we link two halves of a circle together, we're going to be flying. It might not seem sensible or obvious how we're going to make an infinite set within logic. How we're going to make two infinite sets, one of them that can be the edge of a circle and one of them that can be a straight line. All of these things and more are going to be made really clear. 2 dimensions is loads. If you're computing stuff and you have 2 dimensions, you've got one and you've got a higher one, and that's most of what you need. If this gets exciting at all, it's going to be really exciting. That's always been the scenario. If I've done anything remotely good, I've made a crater in mathematics. Okay, we'll get there, inshallah. Peace. Thank you so much. Whoever finds time to listen to logic. We're not going to have any discussion of anything that sucks here. Just pure perfection, just logic and beauty and hope and inventions and things. I'm obviously not doing this for attention. I'm desperately shy, but I admire someone who's got such obscure taste in media. Thank you. Peace.